I don't know if you can see it very well, but this is what I put on the board on Friday. And we're going to be building on this. The columns are called molecular compounds and ionic compounds. Of course, a compound is a repeating unit, okay? But there's an important difference between molecular compounds and ionic compounds as a chemist, and that's kind of where I'm coming at with you guys. So the next topic we need to talk about in part one is this thing called electronegativity. And here, let me just kind of tell you what I think about electronegativity. I'm going to kind of take a water molecule. I'm going to draw it to the side here. We have an oxygen and 2 hydrogens. Okay, that is water. That's a piece of a water compound. The fact that it's a molecular compound means we call it a molecule. Okay, over here, I'm going to take my NaCl. I'm going to do Na, and I'm going to go dot, 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 dot. It's just what I do. And a Cl over there. Okay, this is an example of an ionic compound, so we could call this we would call this a formula unit. Actually, that's one of your homework that you're going to do for Wednesday. Is this repeating unit a molecule, or is this repeating unit a formula unit? Is it a molecular compound or an ionic compound? And the big thing I told you guys is look for the metal. If it has a metal, it's most likely an ionic compound. About 99.5 or 95, I don't know, %. Okay, if it has a metal, it is an ionic compound. Okay. So electronegativity. All right. So we need to today we're going to discuss the nature of this dot dot dot. Okay, or in the case of water, this dash and this dash. What keeps atoms together to make them either a molecule or a formula unit? It's a wonderful thing. We'll be talking more about, I'll just go ahead and call these, we call these chemical bonds. So this is a chem bond, okay, and this is a chemical bond. And we're going to be talking more about chemical bonds. All right, so that sets the stage for this idea, okay. 2 types of chemical bonds. And I'm going to go ahead and draw, I'm going to go ahead and you guys, hopefully I told you we'd be adding to it. So compounds, we have molecular, and we have ionic, okay, and we have all that stuff we did on Friday. I'm not going to redo it. But molecular compounds, okay, contain, when the atoms are joined together, the chemical bonds, CHM bonds, are all covalent. Okay. Now we see something about electrons. We talked about the structure of an atom in Unit 2. So of course you guys would tell me electrons are the outermost subatomic particle of an atom. And the electrons, one of the things we learned about electrons is they are actually responsible for chemical bonding. They are responsible for bonding. The electrons of the 2 oxygen atoms and the hydrogen atom, the electrons of the 2 hydrogen atoms and the 1 oxygen atom in a water molecule, the electrons keep that water molecule together. Okay, so a covalent bond happens when electrons are shared. So I'm going to go ahead and say chemical bonds are all covalent. I'm going to say covalent electrons are shared. Shared between what? Shared between atoms that are connected together. Okay. So if we contrast that to an ionic bond, okay. Now I'm going to go over here. Of course, ionic bond. You see the word, ionic compound, ionic bond. So ionic compounds contain at least, and it's coming up on a slide here, at least 1 ionic bond. And I'll go ahead and say what ionic bonds say. Okay, the difference between a covalent bond and ionic bond is electrons are transferred. They jump ship. We'll talk about why they're shared or why they're transferred and how you know if they're going to be shared or if they're going to be transferred here in a minute. Okay, so ionic bond, if it's an ionic compound, it contains at least 1 ionic bond somewhere in that mess of atoms that are connected together. If it's a molecular compound, electrons are going to be shared all the places where atoms are bonded together. So I thought I'd go ahead and, here it goes. So this slide is what I put on the board. Ionic compounds, okay, compound that contains within that compound, anywhere within that compound, and I kind of think about it, it's like a contamination issue. If you have at least one ionic bond, the darn whole compound is contaminated, the whole compound is ionic. I'll show you an example. We looked at, oh gosh, I can't remember, was it like magnesium sulfate? Let's pick on that. Magnesium sulfate, MgSO4 2, magnesium sulfate. Now remember I said look for the metal, and this is where I said use the periodic table as your friend, so you guys might already know, oh, magnesium's over there, it's a metal, and you're right, it's an ionic compound. But let me just kind of show you just briefly how I think of what magnesium looks like. It basically has a magnesium here, and we said anytime you see the 2 outside the parentheses, that means you have 2 of those units. So we have 2 SO4s, so let's go ahead and draw those, SO4, SO4, oops, yeah. Okay, now remember I kind of told you when I showed you the water and the sodium chloride, I said my solid lines are actually electrons are shared covalent bonds, okay? In my ... I showed you between the sodium and the chlorine in sodium chloride, okay? My convention is anytime you see a ... those are ionic bonds. And anytime you see a solid line, that actually is a covalent bond. So I chose this as an example to just kind of show you that mess of atoms that makes magnesium sulfate. The sulfates, the SO4 units actually have covalent bonds, but there is an ionic bond between that, what we call that central or that middle magnesium, and the 2 sulfates. Okay. Now covalent bonds, a covalent compound has only covalent bonds. So, and don't forget that actually the other day when we talked about divvying up compounds, molecular ionic, I said molecular compounds and covalent compounds are synonyms. All right. So I brought this back. This actually is a slide talking about and kind of set the stage for this idea of electronegativity. Now I think of electronegativity as kind of a tug of war between 2 atoms. Okay, and I talk about atom A and atom B. So there's an atom A and here's an atom B, and they're going to be joined together. Okay, now of course each of the atoms have their nuclei, and each of the atoms have their inner electrons, and each of the atoms have their valence electrons. And so it's going to be kind of a tug of war with regard to, we'll talk more about this, but they want to get what we call 8 electrons, a complete octet. So let's just say that, and by the way, notice that electronegativity, we have a symbol for electronegativity. It's like an X, kind of a fancy X, that's electronegativity. That fancy X, and sometimes you'll hear me kind of lapse into that, actually that is the Greek letter chi, C-H-I, as in the chi T, I guess, okay? Okay, so what if we say atom A has a high electronegativity, a high chi, I love saying high chi, okay? And let's just say that atom B has a low electronegativity, okay? In that sense, this tug of war I'm talking about, actually the electrons, A, since it has a high electronegativity, electrons are drawn to A. And you actually, and we can see this in compounds, that kind of it swells with regard to having its lion's share of electrons. Okay? Now, when I say electrons are pulled to A with the high electronegativity, 2 things can happen. Okay, what can happen is electrons are pulled over there with the high chi. Okay, but they're not entirely what we say transferred. It's possible that these can be shared. I'll put shared question mark. Okay, if they're shared, of course we have a covalent bond. Okay, and if they're shared though, we basically kind of have more electrons over there. I'll go ahead and finish one more thought because I have this A and B up here. If that's the case, as I've drawn this, we would say we would say that this atom A over here with more electrons is what we say partially negative. And we use another Greek letter, the lowercase delta. We use it, I know it's kind of weird, it's like an S, a fancy S with a loop. That's the lowercase delta. We would say it's partially negative. Okay, that's kind of how we do this. And then over here, kind of finishing that thought, this poor B, okay, it basically, some of its electrons were kind of sucked up by A a little bit. Okay, not entirely transferred, they're shared, question mark. Okay, and we would call that partially positive. One last thing before we leave this. If we use the word polar, if somebody is very polar, or I guess the condition bipolar means that you have extremes, okay? But if somebody has a polarizing nature, it means basically they can walk into the room and they can split people into camps, okay? These want to do it and these don't want to do it. Somebody very polar. So we actually call this a degree of polarity. So we call this a polar situation. Okay, so all of that. So electronegativity, when I say chi, I mean electronegativity. When I do the little x, that's electronegativity. It means an atom's ability to attract electrons to itself when it's bonded to another atom. So again, we need to remember our JAG. Okay, remember our JAG. In general, metals have low electronegativities, and nonmetals, which there's definitely the minority, have high electronegativities. Okay? All right. So we have arrows again. So I'm prefacing this. If you look at the periodic table as it's drawn, just take the first 2 rows, knock out the B's, and the last 6, I said rows, I'm sorry, columns. Take the first 2 columns, knock out the middle columns, and take the last 6 columns. That's 8 columns. Those are group A elements. And there's a trend in electronegativity. It goes this way. Electronegativity increases as you get closer to the nonmetals, okay? And electronegativity increases if you're in the same group as you go from the bottom up. So electronegativity kind of increases this way. So usually you'll see me kind of draw it, well, kind of goes, increases this way and increases this way, which is the same thing as that. Okay, so electronegativity. The ability for an electron the ability of an atom to pull electrons to itself. Here's a figure from your textbook you're actually going to use for your homework. Okay, so if you want to put HW up here, you'll be revisiting this. So here are electronegativity values, kind of the height. We got 2 things going on. We have the height that kind of gives you an indication. Okay, and then we also, if you look really closely, you can see, for instance, lead is electronegativity, a chi value. Chi is equal to 1.9 for lead. Okay, so I don't know if you can see that. All right. Here's another electronegativity chart. Sometimes electronegativity values are actually called Pauling values. Linus Pauling actually is a Nobel Prize winner, I think in the area of chemistry or physics. And so he did work and came up with what is the attraction of an atom for electrons that's bonded to another atom. So electronegativity values, Pauling values. Here's yet another one. This is the one that I use. It should be consistent with the other one from your textbook. So I brought mine today to kind of use on a problem we have coming up. So electronegativity, basically you have an atom that's drawing electrons to itself. The higher the value, the stronger that pull. Okay.
Why are the noble gases included in that?
The noble gases are inert. They don't react with other things, so they don't bond to other things. Yep. Okay. So electronegativities. Now, we looked at deltas before. Let's see. Change in temperature. Anytime deltas. Okay. Anytime you see that triangle, that is the Greek. That is the uppercase delta, not the lowercase delta, and it actually means change in. Change in. So we have another delta. So delta chi, like, oh my gosh, so much Greek. So delta chi means what? Change in electronegativity or electronegativity difference. Okay, delta chi is equal to, and are you guys familiar with those lines? Means absolute value of, okay, is equal to, we'll put a big line here, absolute value of the electronegativity of atom A. Remember, we're going to go back to A and B again. Minus the electronegativity of atom B. That's it. Okay, electronegativity difference. So when we look at what we call bond polarity, and we kind of, I threw out the word polarity here a little bit ago. When we try to evaluate each bond, what we have to do is kind of go we have to take that pair of atoms in question, look up their electronegativity values, do a quick subtraction, and come up with a delta chi, electronegativity difference. I'm going to show you the significance of those electronegativity differences here in a minute. So, in general, if you were to go to the closet of elements on the periodic table, and if you were to pick, oh, I guess it's coming up. Okay, so if your electronegativity differences are large, now think of what that means. It means basically you have something that is honking strong with regard to wanting electrons, something that is not strong. So a lot of times what you would expect, and I'll go ahead and put it over here, under ionic bond, electrons are transferred, I'll put high delta chi, high electronegativity differences. And here in a minute, I'm going to go ahead and put a value for that, like when you do your subtraction. If your electronegativity difference is about, I'm going to say greater than 1.7, then go ahead, its electron is transferred. Now, if your electronegativity difference is not 1.7, then electrons are going to be shared, okay? So I'll put delta chi is low, and I'll put less than 1.7, okay? But they may not be shared equally, and I'm going to kind of show you what that means, or we have some words for that. We have words for that. So this is what I started to say a minute ago. If you were to close your eyes, I'll put both these up here. If you were to close your eyes and pick a pair of atoms that you wanted to bond together, okay, and let's just say you were over here kind of into the upper right-hand part of the periodic table, so you ended up choosing two nonmetals. You chose two nonmetals. It happens a lot in compounds. You know, just say you chose sulfur and oxygen, or phosphorus and fluorine, or bromine and nitrogen. If you choose two nonmetals, and if you do that math that I just said, you're going to come up with a delta chi value, usually, of less than 1.7. Electrons are going to be shared. May not be shared what we say equally, maybe a degree of polarity. Okay, so two nonmetals bonded together, you'll end up with electron what we transferred. Now, if on the other hand you choose one nonmetal and one metal, okay, if you do the math, you're going to come up with electronegativity difference of 1.7 or greater. Electron is going to be transferred in that case, and we'll be talking more about what that looks like, but it's kind of like the video we saw a minute ago. That electron is transferred, and then you end up with something, whatever gave the electron becomes positively charged, whatever picked up the electron becomes negatively charged. Okay, and then you have what I call the dot, 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 the ionic bond between those two ions. So if your delta chi is greater than 1.7, which will be the case if you pick a nonmetal and a metal. Now, this might be where sometimes students say, well, there's one more scenario. What about metals and metals? It happens all the time, right? Because your alloys, your metal alloys that we count on, your stainless steels, most of your metals are not in their pure state when they mold them and use them in practical things. Well, metals and other metals basically is a frozen solution. So stainless steel is a frozen solution. There are not chemical bonds that connect those atoms. It's just simply they froze in proximity to each other. Okay. So I kind of put this already up here on the board, I think. So ionic compounds, I said look for the metal, and now maybe this makes a little more sense. If you have a metal, basically metals have low electronegativities, and that metal has given up an electron or two and become what we call a cation, and you have an ionic bond somewhere in there, okay? And on your unit exam, Unit 3 exam, which will be here before you know it, I'll give you a section. You have the homework for this too, that's for a few compounds. You just need to identify, given those compounds, is that formula of that compound representing an ionic compound or molecular compound? And you just need to look for the metal, but this is kind of why. And then the other day, Friday, remember when we wrote this up here, I said hydrogen, consider it a nonmetal for purposes of identifying, okay, whether your compound is molecular or ionic. Okay, so here we have delta chi, okay. So I said 1.7 or greater electronegativity difference, electrons transferred, okay. Now we kind of have some shades of gray here where electrons are shared, okay. If it's pushing up against 1.7, I have a value of 1.2 here. That means that the thing with the higher electronegativity value, that nonmetal, actually it's going to be what we say partially negative. So there's a high degree of polarity. If your electronegativity difference is 1, and actually your textbook does this a little bit different than I do, breaks it out, and I'll just kind of show you that when we look at your homework. If it's around 1, then the thing with the higher electronegativity value, again, is partially negative but not as polar, okay? 0.5, weakly polar, okay? And the cool thing, and it happens, it definitely happens, if basically you look at those two atoms and you subtract their electronegativity values and the difference is 0, you're like, ugh, it's not polar at all, okay? And we call that actually a perfectly covalent bond. Okay, so here are some examples. Oh, I guess this is an example. Okay, so this is just kind of showing you electrons shared equally on the left. In the middle, electrons are shared but not equally. The big fat one, the gold one, you can see actually its electron cloud is what makes it its size. So it actually is partially negative. Remember that lowercase delta? And then the one on the right is partially positive. And then over here, an electron has entirely been transferred. Okay. So here's where, and I'm going to grab my sheet. You guys can look in your notes if you want to. But we're gonna do HCl right quick and NaCl. So for your homework, this is how your homework might work. Okay, I said let's do a delta chi electronegativity difference for the HCl. So what we do is we look up. I usually put the bigger one first. So if you look up the electronegativity value for chlorine, I got 3.0. Electronegativity value for hydrogen, I got 2.1. Okay, so I got, of course, 0.9. So that's polar, right? And then let's do NaCl right quick. The electronegativity difference for right here between those two entities. Okay, if I look up chlorine, again it's 3.0 minus sodium, I got 0.9. Okay, so I got 2.1 is the electronegativity difference. So of course that's greater than 1.7. So electron is transferred from the one that's lower electronegative, the metal, sodium, to the nonmetal, chlorine. That's how that works. So if you want to, in your notes for this one, like I guess it would be down here at the bottom, if a compound's formula contains only nonmetals, remember, hydrogen is considered a nonmetal. Now, I will go ahead and tell you when we get to it where I need to fix that. It's a nonmetal usually. When we talk about polyatomic ions and ammonium, I'll have to kind of backtrack a little bit. But I won't throw that into the mix when I give you that section on your Unit 3 exam. Okay. So let's take a look at the problems that are due. Maybe. They look like this. Okay, so again, this is sort of what your homework's or your exam's going to look like. It's going to have a section just like this. Okay, so classify as ionic or molecular, and there are no curveballs in that, no hydrogens. So my hint is look for the metal. And in music, our symbol for look is the spectacles. Look for the metal. So for 50, it's kind of related to 48. 50 says, do you call these entities, do you call them atoms? Do you call them maze? No. Do you call them molecules, or do you call them formula units? And I'll just remind you, to me, I looked at them, I didn't see any atoms. So if you want to just go ahead and mark no atoms. But molecules are for molecular compounds, molecular CPD, and again, all nonmetals. And formula units, we use that term for ionic compounds, ionic CPD. So the other ones, and then we go on to chapter 10. 78 says refer to this figure, and again, it's kind of small, so however you want to get the Pauling values, the electronegativity values, you can do that. All you got to do is look at there and assign the number. And then 80 is list these in order of increasing electronegativity. And I'll just remind you that electronegativity increases for main group elements as you go across the period, and increases as you go from the in the group from the bottom up. Increases chi. The last one looks like this. Okay. It says refer to this figure and this table, which I have kind of with the green heading up there, to classify these bonds between atom A and atom B. And your choices are pure covalent, and I'll go ahead and I don't use that terminology, but pure covalent, as you might imagine, means the delta chi is 0. Delta chi is equal to 0. Okay. Polar covalent means electrons are shared but not shared equally. You have something partially negative, partially positive. And of course, ionic, that would be what where the delta chi is greater than 1.7. So that's the sort of thing we're looking for. All right. So let's go on and ease into part 2 right quick. I think the drama outside is subsided a little bit. We need to kind of get down the road with this material because Wednesday we're going to be doing a dry lab, which is good, bad, I think mostly good. A dry lab is one where we don't get the chemicals out, but there's 2 topics that I've chosen to do dry labs just so I can make sure you get the material, more likely to get the material, okay? So this week's dry lab is talking about ionic compounds, okay, and we'll actually be talking about how you name them and how you make a neutral, what we call neutral formula unit. So we need to get down the road talking about ionic compounds. So, all right, so we talked about electronegativity. In the case of an ionic compound, it must have an ionic bond somewhere, and electrons have been transferred. Now, at the crux of kind of this electrons being transferred, we're going to have to revisit this idea of electrons and valence electrons, okay? So we talked the other day about, we talked in the previous unit how electrons are configured, and we said that we have inner electrons and then we have valence electrons, okay? And we said that if you want to know what the valence electrons are, they are in the, let's see, the highest n. Remember that? The highest n. They're not necessarily the last added if you're doing electron configuration, but they're the highest n. So here we have kind of a little periodic table down there. And in order to just quickly go to the number of valence electrons without coming up with electron configuration, right? Just for the main group elements, I think I mentioned this before, but I'll kind of reiterate it. All of these guys, first row has 1 valence electron. The 2A has 2 valence electrons. We'll skip the B's for now. We have 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons. Okay, so the group name is the number of valence electrons we have. Okay. All right. So I think I mentioned this before, and actually this came up why there are no Pauling values for the rare gases for 8A. Okay, in order to have an electronegativity value, you have to be able to connect it to another atom, and these rare gases don't want to connect to any other atom. And here's why: these rare gases are already they basically maxed out. They have what we call a complete set of 8 or complete octet. Set of 8 octet. You might have run into that term before. And the 8 actually comes from, for all those rare gases, and we talked about this when we talked about electron configurations, for each of those rare gases, you basically bump up the last electrons added are the 6 electrons in a p subshell, preceded by 2 electrons in that same energy level, s subshell. Okay. So if you add 2 plus 6, of course you get 8. So now we get to kind of dive into again, we're talking about electrons going to ultimately be transferred here. That's what part 2 talks about. And so it's like the video you saw with the sodium and the chlorine. Basically, electrons are transferred and then chemical bonding occurs. So do you guys have this slide here too? I want to look one more time at that NaCl. We got time. The small things gave up an electron. What gives up an electron? What has low electronegativities? The metals. Okay, in sodium chloride, that was the sodium. Okay, chlorine took in an electron. And then it's kind of like, maybe you might intuitively know, if you have something that's positively charged and something that's negatively charged, they're going to be attracted to each other. And so those gray bars here, these gray bars are my dot, 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 dot. These gray bars are ionic chemical bonds. It's a wonderful thing. But just such a okay. So, and ultimately, with this idea of electrons being transferred, I guess I've never seen it otherwise, but the only reason electrons would be transferred would be for something to get what we call an octet, a rare gas configuration. And what we're going to see is that it's easier for metals to kick off actually all of their valence electrons and become like a rare gas, okay? And it's easier for the nonmetals to take in an electron or 2. We'll be talking more about that on Wednesday. Okay, so as we talk about these atoms losing electrons or these atoms gaining electrons, kind of the general name would be monoatomic, as in one atom ion. Because actually in Thursday's lab we're going to talk about ions that have more than one atom, like the sulfate we looked at earlier. Okay, so you have 2 options. You could have the thing that actually is giving up an electron and becoming positively charged. We call that not a cation, a cation, although it does kind of look like cation. So in the case of sodium chloride, that was the Na. Okay, in sodium chloride, sometimes we do, so we could kind of describe the whole idea, the video you saw, we could show it this way, where sodium, okay, is kicking off 1 electron. And in doing so, now that sodium is a +1 charge. So I have sodium kicking off 1 electron and becoming Na+. I have chlorine in that video, actually, is going to take in 1 electron and going to become Cl-. The Na+ is what we call the cation, and it will be your metal. And the Cl minus is what we call an anion, an anion, and that will be your nonmetal. Okay? So I just think it's cool that the nucleus and the nonvalence electrons are just kind of stuck. So it's the valence electrons that kind of come and go. Okay. So notice that I'm kind of qualifying myself a little bit here. The metals with their low electronegativity tend to kick off electrons, like we saw the sodium doing. And the nonmetals tend to pick up electrons. And they'll form negatively charged anions. Okay, well, I think we're going to take a running start at this on Wednesday and then kind of get you ready for Thursday's lab on Wednesday. So, okay? Very good.